Everyone, welcome to this explainer. Today, we're diving into something we all just totally take for granted, but it's actually a massive cognitive leap in childhood development. We are unpacking a super fascinating third-grade textbook chapter called Fun at Class Party to see exactly how human beings learn the fundamental concepts of measurement.
I mean, seriously, think about it for a second. How do we first learn to measure our world? Before you ever knew what a ruler was or, grasped the concept of inches or centimeters, how did you figure out if that massive new couch would actually fit through your apartment door? We all had to start somewhere, right? We just used whatever tools we literally had on hand.
Okay, let's jump right into the textbook setup. We've got this incredibly vibrant classroom scene where the kids are prepping for a party, and they're just using whatever is at their disposal to make sense of their space. Hands, feet, random paper strings, the whole shebang. They're trying to figure out how high to hang a picture, how much bunting they need for the blackboard, basically just mapping out their world.
Section 1. The limits of hand spans.
Let's look a little closer at these informal methods they're using to decorate. They're using hand spans for the tables, footsteps to measure across the floor, and those colorful paper strings for the blackboard perimeters. And honestly, this brilliantly illustrates what we call the egocentric phase of learning. At this stage, we're literally using our own bodies and our immediate physical environment as our tools. It's completely subjective.
But naturally, we hit our first pedagogical hurdle. The book poses a fantastic question. If Lena and Audie use their handspans to measure the exact same table, are they going to get the same measurement? Well, obviously, no way. Audie's handspan might be way wider than Lena's, so to him, the table is fewer hands long. It introduces kids to a really important concept. Human bodies are completely inconsistent.
So, the big takeaway here is that sure, informal measurements like hand spans and footsteps are a totally natural, intuitive starting point. But their subjective nature ultimately creates a massive need for a reliable system. I mean, if you want to build a house or even just successfully decorate a classroom together, you can't rely on everyone having the exact same size hands. You need a formal, consistent standard.
Section 2. The big table problem.
This brings us to the central spatial dilemma of the whole chapter, and it really forces the students to think outside the box. They need to know if a wide table will fit through a narrow door. But here's the catch. As the teacher's note points out, you can't always just bring two objects right next to each other to compare them. They can't just magically pick up this heavy, awkward cable and shove it into the doorway to see if it fits. They have to solve this remotely.
At first, they just eyeball it. One kid looks at the table, looks at the door, and flat out says, "I guess it will not pass through." But visual guesses just lead to debate. Someone else is like, well, maybe if we turn it. To actually resolve the debate, they need cold, hard proof. And here is how they solve it. It's a brilliant three-step process. First, they measure the table's width with a simple piece of thread. Second, they walk that thread over to the door. And third, they compare the thread's length to the door's width. Boom! By using a piece of thread as a physical proxy, they've just made a massive leap in their cognitive development.
This aha moment right here marks the transition from direct physical problem solving to indirect measurement. It's the ability to figure out a dimension by using a common proxy unit, like our trusty piece of string, instead of trying to smash two immovable objects together. It's a real game changer.
Section 3. Upgrading our tools.
Okay, so now that the kids firmly grasp indirect measurement, they immediately run into a new problem. When you start measuring bigger things, like the length of a whole room or the height of a really tall jar, using a tiny short pencil or a little piece of string takes absolutely forever. It's super tedious and leaves way too much room for error. So, the textbook actively prompts them to innovate.
And their solution is so clever. The text says, "Let us double the paper strips by sticking two of them together." Instead of going out and finding a completely new tool, they realize they can just create longer, consistent proxies by doubling up the stuff they already have. Pedagogically speaking, this is spot on, because it perfectly sets the stage for standardized units.
Section 4. Enter the metre rope. This logical progression brings us to the ultimate resolution of our whole journey. To finally replace all those varied footsteps and tape together paper strips, the class is introduced to a universal truth. You can see them here working with a much longer, continuous unit, represented by this really colorful string of lights, to easily measure the larger distances across the room. And that introduces the definition of a standard unit, an absolutely universally accepted, consistent measurement. For this third grade class, it's introduced as a metre rope.
That meter rope finally gives them the unbreakable consistency they've been desperately searching for since that very first flawed handspan experiment.
But here is the absolute genius of the lesson. It doesn't just hand them the rope and say, hey, use this. It actively asks the kids, how many footsteps fit into a meter rope, right? It forces them to take their old, informal, egocentric tool, their own footstep, and measure it against the new formal standard. That hands-on comparison mathematically proves to them why the standard unit is so much better.
Section 5. The evolution of measurement.
Let's just pull back for a second and look at the amazing cognitive journey this single chapter has taken us on. What's so cool about this timeline is how clearly it maps a child's evolving understanding of physical space. Day 1, they are using egocentric tools, like handspans, relying totally on themselves. Day 2, they see the limits there and shift to environmental proxies, like using that thread for the big table. And finally, day 3, they arrive at standardized units, accepting the universal logic of the meter rope. It is literally a perfect microcosm of human scientific progress.
So, as we wrap up this explainer, I really want to leave you with a thought. How often do you still rely on an informal guesstimate in your own adult life? Next time you quickly eyeball whether a piece of furniture will fit in your living room, or you try to pace out a garden with your feet, ask yourself, have you really outgrown the handspan? Thanks so much for joining me, and keep exploring the fascinating ways we learn to measure our world.